You know that smartphone in your pocket or the laptop you're probably watching this on? What if I told you they all run on a basic design that's almost 80 years old? It's true. A single brilliant idea from 1945 is the foundation for pretty much all modern computers. Today, we're going to pull back the curtain on that blueprint, the von Neumann architecture. All right, so here's how we're going to break it all down. First, we'll get into the big, revolutionary idea that started it all. Then we'll peek inside the architecture itself. After that, we got to talk about its biggest problem, the speed mismatch. We'll even check out an alternative design and finally wrap up with why this thing has stuck around for so long. Okay, let's jump in. Picture this. It's 1945. Computers are these giant, room-filling beasts. And here's the crazy part. They could only do one thing. If you wanted it to do something else, you literally had to get in there and rewire it. A total pain. But then, a mathematician named John von Neumann comes along with an idea that changes, well, everything. And this is the genius of it all. It's called the stored program concept. Basically, the idea was, what if the instructions, the program, weren't hardwired into the machine? What if they were just data, just like any other piece of information? This was a total game changer. All of a sudden, you could change what a computer does just by feeding it a new program. It could go from being a calculator to, say, a word processor, just like that. So, the absolute key to making this work is the shared memory. Think of it like a big library. On one shelf, you've got your data, stuff like A equals 10. And right next to it, on another shelf, you've got the instructions, things like ADD or move. The big deal is that they all live together in the same space, accessed the same way. That right there is the heart of the von Neumann architecture. Okay, so we've got the big idea down. Now, let's pop the hood and see how the pieces actually fit together. How does a machine use this shared library? Well, it's all about a few key parts working in perfect sync. The actual flow of information is pretty simple when you look at it. It starts with you, with an input, like typing on your keyboard. That goes straight to the brain, the CPU. The CPU then grabs what it needs from the memory, does its thing, and boom, sends the result to an output, like your monitor. Input, process, output. A super clean, super powerful loop. All right, let's meet the cast of characters. The big one, of course, is the central processing unit, the CPU. That's the brain. Then you've got the memory unit, where everything is stored. Inside the CPU, you've got two critical parts, the arithmetic logic unit, or ALU, that's the number cruncher, and the control unit, which is like the traffic cop for the whole operation. And of course, you need the input and output units so we can actually talk to the machine. Let's talk about the control unit, or CU. This thing is the orchestra conductor. It's not playing any instruments, but it's telling everyone else when to play. It fetches an instruction from memory, decodes it, figures out what to do, and then sends out all the signals to make sure every single step happens in exactly the right order. It's the part that makes sure you don't try to say, add two numbers before you've even fetched them from memory. And while the control unit is directing traffic, the arithmetic logic unit, the ALU, is where the real action happens. This is the mathematical muscle of the CPU. Anytime your computer needs to do some math, add, subtract, whatever, or make a logical comparison, like is A bigger than B, the ALU is what's actually doing the work. It's the system's powerhouse calculator. So how does this all come together? It's through a constant, looping process, kind of like the computer's heartbeat. It's called the fetch, decode, execute cycle. First, the CPU fetches the next instruction from memory. Then, the control unit decodes it to figure out what to do. Finally, the ALU executes the command. After that, a little thing called the program counter points to the next instruction, and the whole thing starts all over again. And this isn't happening slowly. It's happening billions of times every second. Insane. Okay, so this design sounds pretty elegant, right? And it is. But it's not perfect. There's one big built-in problem that engineers are still dealing with today. It's a famous issue, and it all boils down to a traffic jam. So here's the issue. There's a huge speed mismatch. The ALU on the CPU is blindingly fast. It can crunch numbers like nobody's business. But the main memory, it's fast, but it's way, way slower than the CPU. I love this analogy. It's like having a Formula One car that can go 200 miles per hour, but it's stuck in city traffic because the road to the gas station is clogged. The CPU is constantly just sitting there, waiting for memory to catch up. And this exact problem has a name, the von Neumann bottleneck. It happens because both the instructions and the data have to travel down the same single-lane highway, the bus, to get to the CPU. So the CPU can't grab an instruction and the data it needs at the same time. It has to go get one, then go back for the other. That constant back and forth, that's the bottleneck. It's why even the fastest processor can feel slow sometimes. It's just waiting in line. So how do you get around this? Well, engineers came up with a really smart fix: registers. Think of registers as tiny, super-duper fast storage spots built right onto the CPU chip itself. Instead of making that long, slow trip to main memory for every little thing, the CPU keeps the most important, frequently used stuff right there next to the ALU. It's like a VIP lounge for data, and it helps bridge that massive speed gap. Okay, so with this big bottleneck issue, you've got to wonder, is there another way to do this? And the answer is yes, there is. Let's take a quick look at the main alternative design. The other big player is called the Harvard architecture, and its solution to the bottleneck is pretty simple, actually. It just builds two separate roads. Instead of one shared memory for everything, Harvard has a separate memory for instructions and another separate memory for data. With two paths, the CPU can grab both at the same time. No more traffic jam. So why isn't everything built this way? Well, it's more complex and more expensive to build. That's why you mainly see it in specialized things like embedded systems, not your everyday laptop. Right, so if Harvard is faster, why are we still using a design with a known bottleneck? Why does this nearly 80-year-old blueprint still rule the world of computing? It's a great question. It really comes down to two big things: simplicity and flexibility. For one, the single memory design is just simpler and cheaper to make. But the real secret sauce is its flexibility. Think about what you do on your computer. One minute it's a web browser, the next it's a video editor, then it's a gaming rig. It has to be a jack of all trades. And because the von Neumann architecture treats programs just like any other data, it's perfect for that kind of general purpose do-anything computing. And man, has it lasted. I mean, think about it. The idea comes out in 1945. It powers the giant mainframes. It's there for the birth of the personal computer in the 80s. And here we are, decades later, and it is still the fundamental design inside pretty much every single device we use. That's just incredible staying power. And that leaves us with a pretty big question to chew on. For almost a century, we've built our entire digital world on this one design. We've gotten really, really good at patching up its biggest weakness, that bottleneck, with clever tricks like caches and registers. But now, with things like AI and huge data sets pushing computers to their absolute limits, you have to wonder, is this 80-year-old blueprint going to be enough for the future? Or are we on the verge of a completely new way of thinking about computing?